lecture we continue the discussion on line balancing. So this network represents the activities in a typical line balancing situation. So there are 11 activities that have to be performed. One could assume that 11 components or sub-assemblies are assembled to form a final product. Now there is an activity time associated with each of these activities, which are given in yellow, so 4 units, 2 units, etc. Units could be minutes or seconds depending on the assembly. There is also a precedence relationship which is also captured in this network. For example, activity number 2 or say component number 2 cannot be assembled unless 1 is assembled. So 1 precedes 2. Similarly, 1 precedes 4, 4 precedes 5, 3 and 5 precede 6 and so on, which means we cannot do activity 6 unless both 3 and 5 are completed. As we mentioned in the previous lecture, if there is only one person who is actually assembling everything, then this person would take the sum of all the processing times, which is 12, 15, 16, 22, 30, 32, 47 units to assemble each final product. So if one person is sitting and doing everything, it would take 47 time units. If 2 people do it, then at steady state it will be 47 divided by 2. Every 23.5 time units one could get an output and so on. But in general it does not happen that way, because some of these could involve equipment and machinery and testing devices, which we may not duplicate so much. So we would rather have different workstations or benches to which these activities are assigned. So if we imagine a situation where there are the 11 activities and there are 11 workstations or benches, say 1, 2, 3, 4 up to 11, we also assume in this example, as in every line balancing problem, that the order 1, 2, 3, 4 up to 11 is feasible. So if we have 11 benches or workstations with say 11 operators and each person carries out one activity, then the first unit will come out at time equal to 47, but at steady state the output of the system will be the bottleneck, which will be the maximum of the individual assembly times, which would be 8 units. At the same time, we also define something called T, a cycle time, which is the expected output from the system. For example, in this if we say T equal to 12, then the demand is such that we would expect an assembly to come out every 12 time units. So once we define this T, the problem is one of trying to find out how many workstations we require, minimum workstations, such that each task or activity is assigned to only one workstation. The time taken in a workstation does not exceed the cycle time 12, and the precedence relationships among the activities are satisfied. So this is called the line balancing problem. So given a set of activities that have to be performed, given their activity times and the precedence relationships, for a given cycle time T, what is the minimum number of workstations that is required, how these tasks are assigned to these workstations such that the total time taken in a workstation is less than or equal to T, each task is assigned to only one workstation and the precedence relationships are satisfied. Now this is called the assembly line balancing problem. So let us first show a formulation of the line balancing problem, and then we would look at a couple of solutions to the line balancing problem. Now there are 11 tasks, so we could say that there can be a maximum of 11 workstations or 11 benches that we could have, one for each. But then that would give us a feasible solution with 11 workstations or 11 benches, where each activity goes to one workstation and the cycle time would still be less than or equal to 12 in this case, because the cycle time will be 8. Since the cycle time is less than or equal to 12, it is possible to add activities to workstations and thereby try and minimize the number of workstations. So we now start defining the first variable as Sj equal to 1 if workstation j is chosen. We initially assume that a maximum of 11 stations can be used. Maximum of, if there are n activities, we would assume that a maximum of n stations can actually provide us a feasible solution, and therefore we would like to minimize the number of stations. So here we would define j equal to 1 to 11 for this problem, or j equal to 1 to n for a general problem. So we would say that a maximum of 11 stations are there. Now can we bring down the number of stations? Now if we can solve it with 5 workstations, then the solution would take 5 out of the 11 values will take 1, and the remaining 6 out of the 11 values will take 0, saying that these stations are not created. So Sj equal to 1 if station j is chosen or created, and let Xij equal to 1 if activity I is allotted to station j. Is allotted to station j. Now we start writing the constraints. Each activity should go to only one station. So we would have the constraint sigma Xij summed over j equal to 1 for every activity I. Each station, the activity is allotted to a station. The sum of the activity times of the activities allotted to a station should not exceed t. So this would be sigma Ti is the activity time for activity I. So Ti into Xij summed over I should be less than or equal to t for every j. J represents the workstation. So the activities that are allotted to a workstation, the sum of the activity times of those activities should not exceed the cycle time t. More importantly, we can allot an activity to a workstation only when the workstation is chosen. So we redefine it by saying that if there are activities allotted to a chosen workstation, then the times of sum of times of those activities should not exceed t. So the left hand side tells us the sum of the activity times of those activities that are allotted to a station. Now this is the cycle time, but then we could also add an Sj, where Sj equal to 1 when the station is chosen. This also means this constraint would also ensure this is t into Sj. So I will write it as t into Sj for every j. So only when Sj equal to 1 that workstation is chosen and to which activities can be assigned. So you cannot assign activities to a workstation that is not chosen, and for every chosen workstation the sum of the activity times should be less than or equal to t. This constraint also helps us in linking the xij variables with the sj variable. We still have not come to the objective function, we will do that. Right now this links the xij variable with the sj variable. Then we have this precedence constraint. So let us take one precedence which is say 1 and 2. So activity 2 can be assigned only after activity 1 is assigned, it means 1 precedes 2. Now this would mean that if for example we have x11, which means activity 1 is assigned to station 1, activity 2 can be assigned to station 1, 2, 3, 4 up to 11. Now this implies that if 1 and 2 are assigned to the same station 1, the operator will first assemble component 1 and then assemble component 2. So this is modeled as if 1 goes to 1, then x11 should be less than or equal to x21 plus x22 plus x211. This would also, I am sorry, this would mean x11 plus x21 x12 plus x22 component 1 goes, activity 1 is in workstation 1, then activity 2 can go to workstation 1 or workstation 2 or 3 or 4 and so on. But then if for example activity 1 is allotted to workstation 2, then activity 2 should not be allotted to workstation 1, it can be allotted to 2, 3, 4 etc. till 11. So this will be modeled as x12 will be x22 plus x23 plus etc. plus x211. Similarly, if activity 1 goes to workstation 3, then we have x23 plus etc. plus 211. So like this, the last set for this pair would be x111 is less than or equal to x211. So these 11 constraints capture the precedence relationship between 1 and 2. Similarly, to capture the precedence relationship between 1 and 4, we will have 11 other constraints. So we have to first find out what are all the, how many precedence relationships we have. So here we have the number of arcs essentially represent the number of precedence relationships. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13 precedence relationships. Each precedence relationship is between a pair of activities, and then we have to have 11 constraints for each of the precedence relationships, giving us 13 into 11, 143 constraints to handle this. We have just shown the 11 constraints for one particular precedence relationship. Now there are actually better ways of writing the precedence relationships, but we are not going to emphasize on that. The purpose here is only to show how the formulation looks like. There are slightly more efficient ways of reducing this 143 constraints into a lesser number of constraints which capture the same thing. But what we have shown here is the reason or the rationale behind the precedence constraints, where if there is a relationship between 1 and 2, the workstation to which activity 2 is assigned should be a higher numbered workstation or equal to than the workstation to which 1 is assigned. So if 1 is assigned to workstation 1, then 2 can be assigned to 1, 2 up to 11. But if 1 is assigned to workstation 2, then 2 can be assigned only up to 2 to 11. So we cannot have x21 assignment there. So we cannot, this would prevent activity 1 from being assigned to workstation 2, and it will have activity 2 assigned to workstation 1. It will prevent that, because if activity 2 is assigned to workstation 1, through this all of these will be 0, therefore we will have 1 less than equal to 0, and this will prevent activity 2 from being assigned to workstation 1. So we have 11 such constraints which model this precedence relationship, and then we have 13 such precedence relationships. Then the objective function is to minimize the number of workstations. So minimize sigma Sj, j equal to 1 to 11 will be the objective function associated with this. Of course, all xij's and Sj are binary variables, so they are either 0 or 1. So optimally solving this 0 1 problem can give us the optimum solution to the line balancing problem. But then we will look at two very simple heuristics to solve this line balancing problem. One is a heuristic solution which is based on shortest processing time based heuristic. So we would start by saying workstation activity time. So we would say, to begin with, we can do activity 1 only, because all the rest of them have precedence relationships which are related to activity 1. So we start with activity 1, so which goes to workstation number 1, we assign activity 1, and activity 1 has processing time equal to 4. Now that we have assigned activity 1 to workstation 1, 2 and 4 are available now, because activity 1 has been allotted. So we have, let us say, 2 and 4 with us. Now 2 requires a time of 2 units, 4 requires a time of 6 units. So we would assign, based on SPT rule, we would assign activity 2, and then it takes 2 more units. So activity 2 has been assigned, and since activity 2 has been assigned, we have activity 3 that is available now. So 3 and 4 are available. Then with 3 and 4 are available, we can try and assign one of them. 3 requires 3 units, 4 requires 6 units. So once again, based on SPT, so 3 will go here, so plus another 3 units. So since 3 is assigned, we cannot add 6 into the list because 4 is yet to be assigned. So we have only 4 that is available. So we try and put 4 here, but then we realize that the cycle time exceeds 12, because 4 plus 2 6 plus 3 9 plus another 6 is 15. So cycle time exceeds 12. So we create a second workstation and try and put activity 4 here. This goes with time equal to 6. Now when activity 4 is allotted, 5 is the only one that is remaining. So you put 5 comes here, 5 is the only one that is remaining, so 5 goes here plus 1, and once 5 is allotted, 6 can be brought in, so 6 comes here. Now 6 requires 6 time units, so we try and put 6 here, and we realize that it exceeds the value of 12. So create a third workstation with activity 6 with time 6, 6 goes. Now the moment 6 is allotted, we could bring in 7, 8 and 9. So 7, 8 and 9 with 7 has time equal to 8, 8 has time equal to 2, 9 has time equal to 5. So we choose 8 based on SPT rule. So 6 and 8 plus 2, so 8 goes. Now when 8 goes, 10 can come in. So we have 7, 9 and 10 available. 7 requires 8 time units, 10 requires 6 time units, 9 requires 5 time units. Now the smallest is 9 with 5 time units. We try and put it here, but we are not able to because it exceeds the cycle time. So create a fourth workstation with 9 here and time equal to 5. So 9 goes. Then we have 7 and 10. This is 8 and this is 6. So the smallest number is 6. So we take 10 plus 6. So 10 goes. We cannot bring 11 into it because 7 has not yet been done. So now 7 is the only one that is available. So 7 requires 8 time units. Adding an 8 here will exceed the cycle time. Create one more workstation with 7 and time equal to 8. So 7 goes. Now 11 is the only one that is remaining. 11 has 4 time units required, 4. So add 11, 7 and 11, 8 plus 4. So now all the activities are assigned and we get a solution like this. Now the cycle times in each of these are 4 plus 2, 6 plus 3, 9, 6 plus 1, 7, 6 plus 2, 8, 5 plus 6, 11 and 8 plus 4, 12. So based on the shortest processing time rule, we now have a solution with 5 workstations, have a solution with five workstations, and these are the allotments to it. Now the goodness of a solution is measured using two measures, a primary measure and a secondary measure. Now the primary measure is called line efficiency. Line efficiency is, we now have 5 lines with a cycle time of 12 and the maximum is also 12. So 5 lines with 12 cycle time is about 60 time units, and the total of these 47 time units are now made in 5 stations, each with 12 in 60. So line efficiency is 47 by 60, or in general it is sigma Tj or Ti, sum of the activity times divided by n into T, where n is the number of workstations chosen and capital T is the cycle time. So this is 47 by 6. So dividing, 6 sevens are 42, 50, 6 eights are 48. So line efficiency is 78.33%. We also realize that in the line efficiency equation, the numerator is a constant and the actual variable comes only in the denominator with this n, because this is a constant and this n and t, depending on capital T, the n gets defined. So the actual measure is dependent only on the denominator and not on the numerator. Numerator is a constant. Now there is a secondary measure which also tells us how balanced the line is within these 5 workstations. For example, this is going to take 9 units, 7 units, 8 units, 11 units, 12 units. Now even though the allowed cycle time is 12, if some stations take less time and some stations take 12, there is some kind of an imbalance. Now the operator who is working on the workstation which takes 12 units is going to be occupied all the time, whereas the operator who works on this is going to be used he is going to use only 7 time units for every 12 time units, or will be producing excess and building inventory within the line which cannot be consumed because the slowest person is going to take 12. Either this person has to stop working for every 5 time units, or this person will end up building some inventory. There are many things that matter because the input to this is the 9 is that comes from this workstation. So, we all need to ensure that the workstations are sufficiently balanced, so that there is very little difference between these 5 numbers. The closer these 5 numbers are, either the inventory will be less or the idle time will be less. If these numbers vary, as in this example, you will find that either the person has to be idle or the person will end up creating inventory which cannot be consumed. So, there is a measure called Smoothness Index which tries to in this example the smoothness index will be the actual cycle time is 12. So, 12 minus 9 which is 3 square, minus 5 7 5 square plus 4 square plus 1 square plus 0. So, in general the smoothness index formula will be sigma T minus sigma T I x I j whole square. So, this represents the time in a workstation, this represents the cycle time. So, square and sum is the smoothness index. Larger the line efficiency, more efficient is the line, smaller the smoothness index, better it is for the line. So, the solution to a line balancing problem is measured on these two factors, which are line efficiency and smoothness index. Now, let us look at another solution to this problem, which is this heuristic based on longest path in the network. Now, if we take activity 1, the longest path is going to be 4 plus 6 10 plus 1 11 plus 6 17 plus 8 25 plus 4 29 will be the longest path for 1. Once again 4, so you could reach 6 using this, which would give us 5, or using this, which would give us 7. So, 4 plus 7 11 plus 6 17 plus 8 8 and 5 25 plus 4 29. For activity 2, the longest path will be 5 plus 6 11 plus 8 19 plus 4 23. For activity 3, the longest path will be 3 plus 6 9 plus 8 17 plus 4 21. For activity 4, the longest path will be 7 plus 6 13 plus 8 21 plus 4 25. For 5, the longest path will be 1 plus 6 7 plus 8 15 plus 4 19. For 6, the longest path will be 6 plus 8 14 plus 4 18. For 7, it will be 12. For 8, it will be 12. For 9, it will be 9. For 10, it will be 10. And for 11, it will be 4. So, these are the longest paths for the 11 activities that we have. Now, we will sort the activities in the decreasing order of the longest path, and the arranged order will become 1 first with 29, 4 with 25, 2 with 23, 3 with 21, 5 with 19, 6 with 18, 7 with 12, 8 with 12, 10, 9 and 11. So, this is the order of arranging the activities based on the longest path which is there in this network. Now, we use this information and develop another heuristic. Now, such a heuristic would start like this. So, once again we have workstation, activity, and time. So, we start with workstation 1 and activity 1 is assigned to workstation 1 with time equal to 4. Now, the moment activity 1 is assigned, we have 2 and 4 that are available. So, we have 2 and 4 that are available. Now, earlier we chose that activity based on shortest processing time. Now, we will choose the activity based on which one appears early in this order. So, between 2 and 4 you realize that 4 actually appears earlier than 2. So, we choose 4. So, activity 1 followed by activity 4. So, 4 goes, 4 requires time equal to 6. So, 4 plus 6. Now, once 4 is over, then you can take 5 into it. Now, go back and see between 2 and 5 which one goes first. So, 2 goes first, but then we realize that if we add 2 we have to create another workstation, because this requires, we can take 2 here. So, between 2 and 5 2 comes first. So, 2 requires time unit of 2. So, we add time unit of 2 here. So, this goes activity 2 plus time unit equal to 2. Now, once we have activity 2 completed, then we have 3 that is here that comes in. Now, between 3 and 5 3 comes first in this. So, we take 3 requires 3 units. We cannot add 3 into it because it exceeds the cycle time of 12. Create a second workstation with 3 activity 3 and with time equal to 3 units. So, once activity 3 is allotted, we cannot allot 6 because 5 is still to be allotted. So, we allot 5. So, 5 is the only one. So, we do not look at this order, we look at this order only when we have more than one activity available for allocation. So, 5 is the only one. So, it takes plus 1 time unit. So, now 6 is available, 6 is the only one available and 6 can be added here. So, plus 6, 6 also takes 6 time units. Once activity 6 is allotted, we have 7, 8 and 9 that are available. So, we have 7, 8 and 9, we have 3 activities that are available. Now, we look at this order, first it is 7 and then it is 8. So, we take 7, 7 requires 8 time units, 7 goes. We cannot add 11 because we still need to do 8 and 9. Now, between 8 and 9 8 comes first, 8 requires 2 units. So, allocate 8 here, 8 requires 2 units, 8 goes. Now, 10 comes first. So, now 10 comes here next. Now, between 9 and 10 we look at this order and realize that 10 comes ahead of 9. Now, we cannot add 10 there. So, create a fourth workstation and then put 10 here with time equal to 6. So 10 goes. So that brings us 11 into the picture. So that brings us 11 into the picture. So between 9 and 11, 9 comes ahead. So 9 plus 5. So 11 is the only one that remains. So 11 requires 4 time units. So 11 cannot be fit into this. So create a fifth workstation which takes activity 11 and has cycle time equal to 4. So this has cycle time equal to 12, 10, 10, 11 and 4. Now this will have the same line efficiency because there are 5 stations with maximum time equal to 12, same line efficiency, but this will have a larger smoothness index because this would contribute 12 minus 4 the whole square. So this, from a smoothness index point of view, this is not very desirable because it is going to create a lot of variation. So either a lot of inventory or a lot of idleness into the system. Now we can actually do another thing here, which is this. Now the next effort can be in both these solutions. We have a total of 47 time units for allocation, and by choosing 5 workstations and having a maximum time of 12, we have 60 time units available. So the line efficiency was 47 by 60. Now if we have 5 workstations and instead of a cycle time of 12, now if we can have a cycle time of 11, then not only will the line efficiency go up, but the smoothness index will also come down. So the next issue will be, given the number of workstations, can we reduce the cycle time slightly further? So one could think in terms of solving this problem again and using some heuristics to see whether we can actually get a cycle time of 11 instead of a cycle time of 12. Now if we try to do this here, can we get a cycle time of 11 in this? Let us try and do this once again with cycle time equal to 11, and let us do it little quickly. So workstation 1 would get activities 1 and 4 with cycle time 4 plus 6. So if 1 and 4 are allotted, then we have 2 and 5 remaining. 2 and 5 remaining. Now in this order 2 comes first, 2 requires 2 time units. So create a second workstation with activity 2 and time 2. So 2 goes, 5 remains, 3 comes in. Now between 3 and 5, 3 comes first, so 3 can be added here, plus 3, 3 goes. Now 5 is the only thing that is remaining. If 5 is the only activity remaining, ordinarily we would try and put 5 here because this is the current workstation, but we also realize that 5 can actually go here because both 1 and 4 are satisfied. So you could add 5 here to give a plus 1, so 5 also goes, which brings us 6 into the picture. 6 requires 6 units of time, so 6 can go here plus 6, so 6 is over. Then we have 7, 8 and 9. Out of these 7 comes first with time equal to 8. So third workstation, 7 comes first with time equal to 8, 7 goes. Then we have 8 and 9, 8 comes next, so 8 comes next plus 2, so 8 goes, then 10 comes in. Now between 10 and 9, 10 is first, so create a fourth workstation with 10. 10 has time equal to 6, 10 goes, then comes 9, 9 has time equal to 5, and then we need to create a fifth workstation with 11 and time equal to 4. Now both the line efficiency and the smoothness index will be better for this solution, because the line efficiency will be higher, because it will become 47 by 55 instead of 47 by 60. Smoothness index would also be slightly better, because the loads on the workstation are 11, 11, 10, 11, 4. So smoothness index will also be better here compared to this one. So we could, if we end up from the solution, if we realize that the line efficiency is slightly lower, then we could think in terms of, for the same number of workstations that I have in this solution, can I bring down this t by 1 and get a better line efficiency. So we can work on that till we cannot improve the line efficiency anymore. Now there are a few other advantages of using these heuristic solutions. Now if we go back and try to solve this optimally in the way that has been given here, for this particular problem we will have 11 variables for Sj, because we maximum of 11 S's are available, S1 to S11, and then we have another 121 variables for the Xij, and then we have many constraints. This will be for every I, so this will be 11 constraints. This would also be for 11 constraints, and this set will be 11 for each precedence, and there are 13 precedents, so 143 constraints. So if we solve it this way, even though as I mentioned there are better ways of representing this, if we solve it as it is, we are talking of 132 variables and 143 plus 22, which is 165 constraints. So we solve a slightly large binary problem with 132 variables and 165 constraints. Now let us try and map, let us say, this solution into this formulation and see what happens. Now this feasible solution has 5 workstations. So if I try to map this here, I will have a solution. For this I will have a solution which is like S1 equal to S2 equal to S3 equal to S4 equal to S5 equal to 1. So 5 workstations, and I will have X11, X21, X31, X42, X52, X63, X83, X94, X104, X75, X115 equal to 1. That will be the solution when we map it to this. Now what does this mean? This has given me a feasible solution with 5 workstations. So a feasible solution is an upper bound to a minimization problem, and therefore since I have a feasible solution with 5 workstations, I am not interested in feasible solutions with 6. Optimum solution cannot be 6 or 7 or 8 or 9 or 10 or 11. So the optimum solution can have 5 workstations or less. So what I will do is, I will now try and solve to find out if there is an optimum solution with 4 workstations, because already I have a feasible solution with 5 workstations. So I will try and see if I can have an optimum solution with 4 workstations. So if I try and solve it with 4 workstations, then you can see the number of variables and constraints that I will have. Now if I solve for 4 workstations, there will be only 4 Sj values and there will be 44 Xij values. So, Xij will now take only 44 variables, because each of the 11 activities can be assigned to each of these 4 workstations. Now, the constraints Xij, this will be 11 constraints, this will be only 4 constraints, and here for every precedence relationship there will be only 4 constraints into 13. So, I end up having 48 variables and 52 plus 11 63 plus 4 67 constraints, and if the optimum solution is 4, it will give me the optimum solution. So, getting a heuristic solution first actually helps us in getting the optimum solution in a slightly better way. Otherwise, we would be solving an optimization problem with 132 variables and 165 constraints, and because of the heuristic solution that we have, it is enough now that the binary programming to get the optimum solution will have 48 variables and 67, 52 plus 11 63 plus 4 67 constraints. So, it is enough to formulate and solve that problem. Now, in case the optimum solution does not have 4 benches, but has 5 benches, then the optimum would give us infeasible, because we have worked with 4 benches. Then we already know that we have a solution with 5 benches, and therefore, this is 5 benches or 5 workstations, and therefore, this is optimum. If the optimum had a solution with 4 workstations, then it will show that solution. Then we will have to try and see whether a solution with 3 is possible. Now, in order to approach that, we will look at it from a lower bound point of view, because total time required to assemble is 47, and if we have 12 as the cycle time, then the minimum number of workstations, which is a lower bound, is 47 by 12 upper integer value, which would give us 4. So, there cannot be an optimum solution with 3 for this case. So, the only case that we have to look at is, can we have a solution with 4 workstations, which means it is enough to solve this problem with 48 variables and 67 constraints. And if we actually do that, we get an optimum solution to this problem, which will look like this. So, the optimum solution is like this. So, the optimum solution has 4 workstations. So, workstation 1, activity and time. So, 1, 2 and 4 with 4 plus 6 plus 2. Station 2 is 3, 5, 6, 8 with 3 plus 1 plus 6 plus 2. Station 3 is 10 and 9 or 9 and 10 with 6 plus 5, and station 4 is 7 and 11 with 8 plus 4. So, this is the optimum solution to this particular problem, where we have 1, 2 and 4, once again precedence are satisfied, 3, 5, 6 and 8, 3, 5, 6 and 8 precedence are satisfied, 9 and 10 precedence are satisfied, 7 and 11 precedence are satisfied. So, the cycle times here will be 4 plus 6, 10 plus 2, 12, 12, 11, 12 with total equal to 47. Line efficiency is equal to 47 by 4 into 12, which is 47 by 48, which is the best that is achievable. And smoothness index this is about 98%. The smoothness index will be 12 minus 12 the whole square plus 12 minus 12 the whole square plus 12 minus 11 whole square plus 12 minus 12 whole square, which will be 1, which is the smallest that is possible. So, this is how we solve the assembly line balancing problem. So, we first try and find out, given a cycle time, what is the minimum number of workstations that are possible. Now, if we get to the optimum solution, we first, in order to make the optimum solution a little simpler in terms of number of variables, we first try and get a heuristic solution like what we have shown here. So, for 11 activities we got a heuristic solution with 5 workstations, and therefore, we try and solve the optimum solution case with 4 workstations. So, that if there is a solution it will show, if the optimum is 5 then it will show infeasibility. Or alternately we could actually do it with 5. So, the number of variables and number of constraints will increase slightly, and then if the optimum is 5 it will show up as 5, if the optimum is 4 it will show up at 4, and so on. In fact, if the optimum were 3, which is not possible in this case, when we solved it for 4 stations, if we could get a solution with 3 it would still show the 3, but in this case it is not possible because the total is 47 and the cycle time is 12. So, a minimum of 4 workstations are required. So, the main problem is to minimize the number of workstations for a given cycle time. The next problem, if we were to look at only heuristic solutions, is to try and get, invariably the heuristic solution will overestimate the number of benches slightly, and in such a case the problem will then be, for a given number of workstations can I reduce the cycle time further, so that the line efficiency can go up, the smoothness index can come down. But the basic problem is always one that minimizes the number of workstations for a given cycle time. So, with this we come to the end of certain production control related decisions. We have seen some aspects like scheduling as well as line balancing. Now, after this we will start looking at some aspects of location decisions. How do we locate plants from a manufacturing and supply chain point of view, and layout decisions as to how, what are the algorithms and methods by which we can have relative location of facilities inside a given location. So, these aspects related to location decisions we will see in the next lecture.